Okay, so when we last left off, we were looking at the organization of the periodic table. We were looking at the organization of the periodic table in terms of metals, nonmetals, and metalloids. Now we're going to look at major classes of elements in the periodic table, and these primarily include groups, periods, and the periodic table. Okay, so to start us off, I gave you a sample periodic table. And the periodic table is organized into groups and periods, okay? A period is a row of elements arranged in order of increasing atomic number and atomic mass. Okay, so periods, they are horizontal, they are rows. Groups are columns of elements with similar properties and reactivity. The periodic table is organized based on element properties and reactivity. Elements of the same group have the same or very similar properties and reactivity. Now, each group has certain letters and numbers associated with it. Main group elements, so main group elements have the group letter A, while transition metals have the group letter B. So just to annotate the periodic table that we have been provided, these numbers associated with each row, indicate the period number, which will be important later on when we start discussing electron configuration. The vertical numbers and letters are group numbers. So 1A through 8A are known as main group elements, while elements with a B symbol, the elements found in this center transition block of the periodic table, so 1B through 8B, are known as transition metals. Okay, we'll start to drill down and focus on the major groups and periods in the periodic table. So let's continue on with this, and let's talk about the named groups. So we know that the periodic table is organized into groups and periods. For groups, these are columns of elements with similar properties and reactivity. So for our named groups, we have the alkali metals. These are group 1A elements. These are highly reactive metals, and these are great electron donors. These, in general, love to react with water. So 1A, So 1A elements, these are our alkali metals. So when you think 1A, I'd like you to think alkali metals. Our 2A elements are known as alkaline, as in alkaline water, earth metals. These are your group 2A elements. These are water reactive metals that generate an alkaline solution when dissolved in water. So going to our periodic table, our 2A elements, let me use a different color for that just to distinguish them. Our 2A elements are known as alkaline earth metals. Would someone like to give me the symbol for one of our alkaline earth metals? What's an example symbol for one of our alkaline earth metals? Yeah, beryllium, or Be, is a good example of an alkaline earth metal. It's in group 2A. Other examples would be magnesium, calcium, strontium, and barium. Perfect. So everything in this column, everything in this group 2A is an alkaline earth metal. Wonderful. Now let's look at some of the more dangerous groups in the periodic table. Group 7A is known as the halogens. So these are strong oxidizing agents and great electron acceptors. These are also in general quite poisonous and toxic elements. So everything in group 7A, so when you see 7A elements, I want you to think halogen. Would someone like to give me an example of a halogen? What's an example of a halogen? Iodine, fluorine, both are reasonably valid. Perfect, perfect. So that looks great. So let's now look at another very important set of elements, especially when we start to think about reactivity, and that is our noble gases. These are group 8A elements, and these are unreactive inert gases. So our group 8A elements are known as the noble gases. And noble gases in general are relatively unreactive or inert gases. An example of a noble gas would be helium, neon, argon, krypton, and xenon. You may want to be especially familiar with these noble gas symbols and names, as they show up a lot when we start to write electron configurations and noble gas or abbreviated electron configurations. So these are the major named groups of the periodic table that you're responsible for. Remember, as just a refresher, just one more time, our 1A through 8A elements are known as main group elements, while our 1B through 8B elements are known as our transition metals. Okay. So these are the major groups of the periodic table, which are essentially major sets of elements that have unique properties and reactivity. Elements in the same group have the same properties and similar reactivity.
Professor?
Yes.
On the noble gas, on the 8A, the last one, the RN, that one is not a noble gas?
Oh, it is as well.
Oh, same thing with the alkaline metals, the RA?
Yep, exactly right. Everything in the same column belongs to this group.
And for the alkaline metal, the 1A is just the first one?
For the alkaline metals, it's also everything in this group. So.
Okay, got it. Thank you. I was confused.
So these group names and numbers indicate that every element in this column has similar properties and reactivity.
Got it. Thank you so much.
Yep, no problem at all. So continuing on, here's the type of periodic table that you'd receive on an exam or you'd be able to use on an exam. So you have to be able to very quickly identify the major groups and write out the major group numbers. Okay. So for example, if I just received this periodic table and I was going to start my exam, first I'd put my standard group number notation. Okay. And then I could quickly identify my groups. So 1A are my alkali metals. 2A, we have our alkaline earth metals. 3A, 4A, 5A, and 6A don't have a unique name that you'll need to memorize. 7A elements are known as our halogens, and 8A elements are our noble gases. So really quickly, just given a basic periodic table, we're able to fill in our main group numbers and fill in our group names. So, just as a reminder, this number above each column is known as the group number. And it's important to be able to identify a group number as it's tied to common periodic trends. So let's take an example. Let's look at an example. So we're asked to work through the following 3 little questions. So in this first example, we're asked to identify the group number or group name for each element. So for bromine, I'm going to go over to bromine, and I see bromine is in group 7A. Okay, so I'm going to write group 7A, and that means bromine is best known as a halogen. Likewise, or in a similar process, I should say, for neon, I go and find neon. It's in group 8A, and we call group 8A elements noble gases. So we've identified our group number and our group name for each of these 2 elements. Let's look at another example. Here we're asked to find the atomic symbol for a period 2 group 5A element. Okay, let's unpack this a little bit. The period number, so period, refers to horizontal rows, while the group number refers to the column. So given the period and group number, we can quickly find our element. So I'm going to go to this period 2, so 1, 2, we're looking at our second row, and then group 5A. So I go to period 2, group 5A, and that gives us nitrogen. So the period number is the row number, the group number is the column number. So the symbol for a period 2 group 5A element would be nitrogen. Okay, and let's look at the last type of example. So we're asked to identify which of the following 2 elements in the list have similar properties. So when we're discussing similar properties and reactivity, what we're really looking for is group, because the periodic table is organized in groups of elements, columns of elements with similar properties and reactivity. So when I'm asking for 2 elements with similar properties, I'm looking for 2 elements with the same group. So from this list, the one thing that stands out to me is this bromine and iodine. If we look in our periodic table and we find bromine and iodine, are bromine and iodine in, oh, sorry about that. Are bromine and iodine in the same group in the periodic table? Are bromine and iodine in the same group? Yes. So would we expect bromine and iodine to have similar properties and reactivity? Would we expect these elements to have similar properties and reactivity? Perfect, perfect. So we'll circle the following 2 elements. Okay, so now that we've seen some examples of problems relating to reading the periodic table, I'd like you now, here's your own copy of the periodic table, just like that which you'd receive on an exam. And I'd like you, given this periodic table, to try to answer the following 3 questions. So question 1, I'd like you to identify the group number and group name for each element. Question 2, I'd like you to tell me the atomic symbol for a period 3 group 6A element. And for question 3, I'd like you to tell me which 2 elements in this following table would have similar properties and reactivity. So let's take about 4 minutes to work on this example, 4 to 5 minutes, just to be generous with the time provided. And from there, I'd like to see some responses either in the chat or verbally for each question. Make sure to note the question number so I can provide feedback. And then we'll discuss this example in about 5 minutes. And if you have any questions at all, don't be shy to type them in the chat or to unmute and ask your questions verbally. And we're already seeing some reasonable responses in the chat. Make sure to identify which question you're answering so I can provide feedback. And remember, just to be careful with assigning your group numbers. And the responses I'm seeing in the chat look great so far. Let's try to get a few more responses, and don't be shy if it takes you a little bit more time to come up with your response and check your work. And we'll go over these problems together in about another 3 to 4 minutes. But the responses I'm seeing in the chat look great. It definitely appears like students are doing the pre-lecture reading, which is quite encouraging to see. But the responses I'm seeing in the chat look great. And we'll discuss this example in about another 2 to 3 minutes. Let's try to get a few more responses in the chat or verbally. And it's okay if your response differs from your classmates. The more responses we have, the more I can begin to understand where the class is at and how to provide feedback to help everyone better approach the material, or to think about the material from an alternative perspective. So don't be shy if you have a response that seems a little bit different than the other responses in the chat. And we'll discuss this example in about another 1 to 2 minutes. Let's try to get a few more responses in the chat, or if you're unsure, a few questions either in the chat or verbally. And just as a reminder, all these Zoom sessions are required as part of our synchronous instruction. And for those who are on the wait list, make sure to continue attending these synchronous sessions as students are added to the course. So, as we've seen a reasonable pool of responses, so let's start with, and we even have more wonderful responses in the chat. Let's start off with magnesium. So going to magnesium in the periodic table, let's put in our modified group numbers. These are the ones that are found in our group number annotated periodic table. So magnesium falls in group 2A, and this is known as the column or the group of alkaline earth metals. So magnesium is a group 2A element, and it is an alkaline earth metal. Wonderful. So looking at carbon now, carbon isn't in a named group. It is simply found in group 4A. So let's just write that down. Perfect. So now for the atomic symbol for a period 3 group 6A element. So we're looking for an element in the 3rd row and the 6th column. So 1, 2, 3. So we have period number 3, and then group number 6A. And that in turn gives us sulfur. So it's in the third row, sixth column, period 3, group 6A. That gives us sulfur. Okay, continuing on. We're asked to find which of the following two elements have similar properties. And immediately, from my experience, my eye gravitates towards phosphorus and arsenic. Why? If we look at phosphorus and arsenic, are phosphorus and arsenic found in the same group? Are they found in the same column of the periodic table? Yes. So then we'd expect phosphorus and arsenic to have similar properties and reactivity. Not exactly identical, but very similar properties and reactivity. And we'll see this when we start to talk about periodic trends and we start to talk about electron configurations. Does this make sense to everyone so far? Does this make sense to everyone so far? Any questions?
I have a question on number 2. Can you go over that one really quick again?
Sure. So the period number is the row number. The group number is the column number. So we're asked to find a period 3 group 6A element. So we go to the third period, the third row in our periodic table, and we're looking for a group number 6A. So we go to the sixth column in the periodic table, or more specifically, the column with the group 6A designation.
Okay.
And then we trace across from the third row all the way to our sixth column, and that gives us sulfur. Does that make sense?
Yes, I have a question. So like on the rows is the numbers right there on your left-hand side. And those rows go all the way down to where the francium, is that how you say it?
Yep. And they increase from 1 all the way to 7. Yeah, they increase as you move down.
The bottom ones, the colorful ones down there, starting with
These are known as lanthanides and actinides, and they're an extension of the 6th and 7th row.
Okay.
Does that make sense?
Okay, yes.
Perfect.
Okay, already got it. Thank you.
Sure. Awesome. Are there any other questions I can address on these examples? If not, let's continue on now, and let's talk a little bit about molecular and atomic elements. So elements can either be atomic or molecular. So our atomic elements, these are elements that consist of a single atom as part of their element formula. These are primarily our metals and our noble gases. So examples of this. So would someone like to give me an example of a metal? What's an example of a metal found in our periodic table? What's an example of a metal? Sodium, sure. So sodium is an atomic element. So its formula would just be written as sodium solid. Don't worry about where we got the solid yet for now. Just focus on the fact that sodium, as it's a metal, is an atomic element, and we just have one atom as part of its chemical formula. Okay, what about a noble gas? What about a noble gas, which is a group 8A element? What's an example of a noble gas that we can use? I see in the chat we have neon. So again, neon is a noble gas and it's an atomic element. In its formula, we have only one atom. So for example, neon, if we're looking at a picture of neon, would just have one atom as part of its chemical formula. So neon would be written as neon gas. Now let's look at our molecular elements. Let's look at our molecular elements. Our molecular elements are primarily our nonmetals as well as our metalloids. elements, and there are different subclasses of molecular elements. The first of which are our diatomic elements, di meaning a prefix of 2. So diatomic elements have 2 atoms as part of their chemical formula. The major diatomic elements are your halogens, oxygen, nitrogen, and hydrogen. Other notable diatomic elements, the ones that I would especially prefer that you memorize, you want to be familiar with hydrogen, nitrogen, and oxygen, because these show up commonly in chemical reactions. So let's start with a halogen. What's an example of a halogen? Fluorine, sure. So because fluorine is a diatomic element, fluorine, rather than being written as F gas, instead, to reflect the fact it's a diatomic element, there are 2 atoms as part of the chemical formula, we write the formula of fluorine as F2. This is saying in fluorine's formula, we have 2 atoms of fluorine. Other examples of diatomic elements would be hydrogen, which is written as H2 gas, oxygen, which is written as O2 gas, and nitrogen, which is written as N2 gas. So all of our halogens are diatomic, as well as hydrogen, oxygen, and nitrogen. Does this make sense to everyone so far? Does everyone see how diatomic, 2 atoms as part of the formula, 2 atoms as part of our molecule of each element? Now, the other designation for our molecular elements would be polyatomic elements. These have 3 or more atoms. And the 2 polyatomic elements I want you to be familiar with are sulfur and phosphorus. Yeah, so the majority of nonmetals are molecular elements. Yes, that is correct. Sulfur, for example, is a polyatomic molecular element that has a formula of S8 solid. So when we're referring to sulfur, sulfur exists in its molecular form in nature, where a molecule of S8 has a total of 8 sulfur atoms bonded together. We won't worry about the exact connectivity of atoms. For now, I'm just showing that S8, the subscript tells us we have 8 sulfur atoms. The other polyatomic element that I want you to be familiar with is phosphorus. So phosphorus, otherwise known as P4 solid, is a polyatomic element where we have 4 phosphorus atoms chemically bonded together as part of its molecular formula. So you should be familiar with the formulas of each of the common atomic, diatomic, and polyatomic elements, because you need to know how to effectively write chemical formulas in order to begin to start to write out and balance chemical equations. Okay, so let's now move on. Any questions before we continue on with today's lecture? Any questions before we continue on?
So the sulfurs that you circled, all those 8, and then the phosphorus, all those 4, those are called molecular elements?
Yes, so sulfur and phosphorus, they're molecular elements, but more specifically, they're known as polyatomic elements. Poly because they have 3 or more atoms in their formula. Does that make sense?
Yes, but what was the, am I right on the molecular elements when we see them like this, categorized as that way? Is that how we refer to molecular elements?
Yes, so sulfur and phosphorus are molecular elements. They have more than one atom as part of their chemical formula, and sulfur and phosphorus are nonmetals. Yes, that is correct.
Okay.
Mhm.
Thank-
Any other questions I can address? If not, let's continue on now. And let's start looking at the physical states of elements. So the state symbol indicates the physical state of each substance. S for solid, L for liquid, G for gas, and AQ for aqueous, which essentially just says dissolved in water. Now, for our metals, metals are solids at room temperature. So for example, we write sodium as sodium solid, aluminum as aluminum solid, zinc as zinc solid, calcium, for example, which is another metal, would be written as calcium solid. And the way that I know to write calcium as calcium solid is because we know that metals are first and foremost atomic elements. They have one atom as part of their chemical formula, and metals are solids at room temperature. The only exception is mercury, where mercury is a liquid. Okay, so metals are fairly straightforward. If you had to take a guess, the majority of elements in the periodic table are in fact, the majority of the elements in the periodic table are in fact solids. So for our nonmetals, we have our noble gases, hydrogen, nitrogen, oxygen, fluorine, and chlorine. All of these elements are gases that we'd write with a G symbol. So for example, if we're writing the formula of a noble gas such as neon, it would be written as neon gas. Hydrogen, nitrogen, oxygen, and fluorine, these are all diatomic gases. From our nonmetals, only one of our nonmetal elements is a liquid, and that is bromine. So bromine is a liquid at room temperature, so we write it as Br2 liquid. Finally, in general, most other nonmetal and metalloid elements are solids. So for example, iodine would be written as I2 solid. Any other questions on this example? Any other questions on this example? So in general, most elements are solid at room temperature. Just as a refresher, metals are solids, mercury is a liquid. Your noble gases, hydrogen, nitrogen, oxygen, fluorine, and chlorine are gases written with a G symbol. And depending on whether we're dealing with a noble gas or a nonmetal, we either have an atomic species, an atomic gas, or a diatomic or molecular gas. Bromine is the only nonmetal that it's a liquid, and every other nonmetal and metalloid is going to be a solid at room temperature. Does this make sense to everyone? Any questions on assigning physical states to elements? You're going to need to be familiar with these physical states, both in order to understand what a sample of an element looks like at room temperature, and to begin to write valid chemical formulas and chemical equations. Any questions before we move on to the next part of today's lecture? If not, okay. Let's take a moment and let's try to write the formula and physical state for the following elements. And I'll start us off here. So first and foremost, Na. So this is referring to sodium. Okay, so we know that it's a metal. So for metals, metals exist as atomic elements and are solids at room temperature in the majority of cases. Oxygen, that's referring to the element with the symbol O. You're going to need to be familiar with, as I discussed last lecture, with both the names and symbols of the first 36 elements, including and iodine as well. So for oxygen, we know that oxygen is a non-metal. It's on the right-hand side of the periodic table. And oxygen specifically is a diatomic element. And we also know that oxygen is a gas from the rules that we discussed earlier. So we'd write the formula of oxygen as O2 gas. Perfect. Hydrogen, that's referring to the element with the symbol H. Hydrogen is also a non-metal. It's diatomic, and it's a gas. So we'd write hydrogen as H2 gas. For our last element in this problem set, we're looking at sulfur, which is the element with the symbol S. So sulfur is a non-metal, but what's unique is that it's a polyatomic element. And in general, the majority of elements in our periodic table are solids. So sulfur has a unique formula of S8, and it's given the solid designation. So there we go. We have the formulas and physical states of each of these four elements assigned using our provided rules. Any questions on this example? Any questions on this example?
Professor, how do we know that sulfur is a solid again?
So based on the rule at the bottom of our page, most other non-metal and metalloid elements are going to be solids.
Oh yeah, okay, got it.
So in general, if it's not an element that I've explicitly told you has a gas or liquid state symbol, you can assume the state symbol will be a solid at room temperature. Does that make sense?
Yes, thank you.
Perfect. So let's now take a look at the following four elements, and let's try to assign the formula and physical state for each element. And we'll discuss this example in about 3 to 4 minutes. And don't be shy to share your responses in the chat or verbally, or you can share a question in the chat or verbally. And we'll discuss in about 3 to 4 minutes. And let's try to get some responses in the chat and make sure to indicate which number you're responding to. And make sure to not just write the physical state, but also the formula, following our rules for writing the formula of common elements. And remember, before you assign the formula, try to think, is this a metal, non-metal, or metalloid? Or is this element listed in any of the lists of my diatomic or polyatomic elements on the previous 2 lecture pages. And let's try to get a nice pool of responses in the chat, or if you're unsure, some questions in the chat, and we'll discuss this example in about another 3 to 4 minutes. And just be really careful and double check your state symbols and your formulas using the earlier 2 reference sheets. And it's great to see a pool of responses. Let's try to get a few more responses before we discuss in about 2 to 3 minutes. And we're seeing some reasonable responses in the chat. Again, just make sure to go over your proposed responses and just double check that the formulas and state symbols match those provided on the earlier 2 pages. It takes some practice getting used to the names, formulas, and physical states of each of these elements, but this practice will be invaluable once we start dealing with chemical equations. And the responses we're seeing in the chat look quite good. And remember, in general, the majority of elements in our periodic table not listed as a gas or a liquid will be a solid. And we're seeing a nice, reasonable pool of responses in the chat, and we'll discuss in about another minute. Okay, so let's discuss this example. So, first and foremost, so looking at barium, Ba, we know that barium is a metal. So from this information, we know most metals, barring mercury, are solids, and we know most metals are atomic elements. So we'd write the symbol for barium as Ba solid. So bromine is a non-metal, and we also know that it's a halogen. From this information, we know from our notes that halogens are diatomic, and bromine is one of the exceptions that we need to know and be familiar with, in that bromine is one of the few elements that's a liquid at room temperature. Looking at xenon, xenon clearly is a noble gas. And we know that noble gases, as in their name, are atomic gases. So we'd write xenon as Xe gas phase. Finally, phosphorus is a non-metal. And phosphorus is one of the few elements on our list of polyatomic elements. Phosphorus has a formula of P4, and in general, most elements in our periodic table, if I haven't explicitly told you what the state symbol is, most elements in the periodic table will have a solid symbol. Most elements in the periodic table at room temperature are solids. Does this make sense to everyone? Does this logic make sense? Any questions on this example? So the number indicates the number of atoms in the formula for that element. So Br2, bromine is a diatomic element because we have 2 atoms of bromine in our chemical formula. The 2 is saying we have 2 bromine atoms in the formula. Did that answer your question? So when we say diatomic, we mean 2 atoms. When we say polyatomic, we mean 3 or more atoms. With this subscript number here indicating the number of atoms found in the chemical formula. Did that answer your question? Is there something I can clarify further in your question? So that you'll have to memorize the common diatomic and polyatomic elements. We'll see later on when we talk about Lewis structure and bonding that there's a clear reason from the perspective of chemical bonding why bromine has 2 atoms in its formula. But in terms of the diatomic, polyatomic, and monoatomic elements, that is something you'll have to memorize and be familiar with. You can tell bromine is diatomic by virtue of the fact it's a halogen, as all elements in group 7A are diatomic. So we have our fluorine, chlorine, bromine, and iodine. Perfect. So let's keep going now and let's look at elements and compounds. So we've been talking a lot about elements, and an element is defined as a pure substance that cannot be chemically decomposed to its component elements. So you can't take an element and get out a simpler element. So no matter how hard you try, if you take sodium, you're not going to get any element simpler than sodium. So sodium cannot be chemically decomposed into simpler elements. However, compounds are empirically defined or experimentally defined as a substance that can be decomposed into their component elements. So for example, if you take sodium chloride, which is of the formula NaCl, table salt, and you apply an electric current, and a lot of heat, you can actually break down sodium chloride into its component elements. In this case, we're taking sodium chloride, which is a compound, and under the right conditions, we can decompose sodium chloride to yield sodium and chlorine, which are elements. So a compound, and this is critical, can be decomposed to simpler component elements. Does that make sense to everyone? Now, if you're curious why we have these very experimental or empirical definitions, that's because in the early stages of chemistry, when we were investigating and isolating elements, The only really reliable method that we had if we were looking at a new substance to identify whether we're dealing with a pure element or a compound is to systematically try and decompose that substance into a known pure element. So that's why this first definition of a compound is based on decomposition and reactivity. Now, a simpler definition that I would recommend that you use for a compound is a substance containing two or more different elements, covalently bonded or with an ionic bond, or ionic, or containing an ionic bond. So an example of this would be sodium chloride, solid. This is an example of an ionic compound. We'll talk more about that later. Another example would be carbon monoxide, which is an example of a molecular compound. In this case, we clearly have two different elements bonded together. So compounds, two or more different elements bonded via either a covalent or an ionic bond. Does this make sense to everyone so far? Compounds, two or more elements. Any questions on that? If not, let's now delve into this ionic and molecular compound distinction, or ionic and covalent compound distinction. So first and foremost, compounds can be either ionic or covalent. Now, to talk about ionic compounds, we first need to define the word ion. An ion is a positively or negatively charged atom, which is known as an atomic ion, or a charged molecule, which is known as a polyatomic ion. So to give us an example of an atomic ion, an example of an atomic ion would be calcium 2+. Okay. Now, one thing to note, we call our positively charged ions, we call the positively charged ions cations. So calcium 2+ would be an atomic cation. Alternatively, our negatively charged ions, such as, for example, Br-, our negatively charged ions are known as anions. So this would be bromine, Br-, which is formerly called bromide, is known as an atomic anion. If we wanted to look at a polyatomic ion, polyatomic ions are molecules with a net charge. So to give an example of a polyatomic ion, one example would be cyanide, which has the formula Cn-. So cyanide would be an example of a polyatomic, in this case, a polyatomic anion. We have a molecule with a net charge, and in this case, because it has a negative charge, we call it a polyatomic anion. Does this idea make sense to everyone? That ions are charged atoms or molecules, positively charged species, cations, negatively charged species, anions. Now, why is this important? Well, ionic compounds are a subclass of compounds that in turn are composed or comprised of a positively charged cation and a negatively charged anion. Now, overwhelmingly, Ionic compounds are composed of a metal cation and a non-metal anion. So an example of this would be sodium chloride, where we have our metal cation, and for chloride, we have our non-metal anion. So sodium chloride is a textbook ionic compound. Now, we don't just have to have a 1-to-1 ratio. We can also have formulas where we have different numbers of our cation and anion. An example of this would be aluminum oxide, which is formed from an ionic bond between a set of aluminum cations and oxygen anion. So in this case, we have oxygen as our non-metal anion and aluminum as our metal cation. So aluminum oxide is another example of an ionic compound. Now, one word that's commonly used in relation to ionic compounds is the word formula unit. I just want you to think, when you see the word formula unit, I want you to think the simplest formula of an ionic compound. So if we look, for example, at sodium chloride, so the simplest ratio of ions in this case involves 1 sodium and 1 chlorine atom. Or more specifically, 1 sodium cation and 1 chloride anion. And what we can do is we can take our simplest ratio of ions, and when we're thinking about ionic compounds repeat this simplest ratio of elements, simplest ratio of ions, in order to generate a more complicated lattice structure. So we take our common repeating unit of sodium and chloride, and what we do is we repeat this unit multiple times, millions upon millions of times, and these lattices, these repeating structures containing our cation and our anion are what make up our ionic compounds. So we take this smaller repeating unit of our cation and anion, this smaller formula unit, and upon repetition, we are able to generate a complicated lattice structure. So just to boil this down to the simplest thing that you need to know, the formula unit is the smallest repeating set of ions in our ionic compound. So for sodium chloride, the formula unit would be NaCl. Does that make sense to everyone? Does this discussion of ionic compounds and formula units make sense so far? If not, let's look at our next subclass of compound, and this is short, sweet, and to the point, covalent or molecular compounds. So the formula unit is just the simplest formula, simplest ratio of ions. And it's in general going to overwhelmingly match the chemical formula for that ionic compound. The reason why I talk about formula units is some questions and some problems ask you to calculate formula units, and a formula unit is almost identical to this idea of a molecule of ionic compound. Did that address your question? Okay, so let's look at covalent and molecular compounds. We have two or more atoms of different elements covalently bonded together. So covalent and molecular compounds are composed of two or more nonmetals. Two or more nonmetals, and they're neutral with no charged ions. So examples of a covalent or molecular compound, one example would be water, H2O. Another example would be nitrogen dioxide, or NO2. In either cases, we have two or more atoms of different elements bonded together, and each of our elements are non-metals. And each of our component atoms are neutral. We have no charged ions. Any questions on covalent and molecular compounds? If not, let's keep going now. So just as a recap, pure substances are a superclass. They describe any species with a fixed, definite composition of elements. Pure substances can be broken down into elements or compounds with our key deciding factors between one, first, the number of atoms of different elements, and number two, whether or not we can decompose that pure substance into simpler elements. Compounds contain two or more different elements, and compounds can be decomposed. Elements cannot. Elements are then split into atomic or molecular elements. For molecular elements, we have two or more atoms. For atomic elements, we just have one atom as part of its formula. Compounds can be either molecular, in other words, covalent, or ionic, and the key deciding factor is that molecular compounds have two or more nonmetals, while ionic compounds contain a metal plus a nonmetal. So this is just a nice little summary to help you remember our rules for classifying substances. Let's now apply these rules, and let's talk about classifying. Let's talk about classifying pure substances as ionic compounds, covalent compounds, and atomic elements and molecular elements. So let's first look at HCl, or hydrochloric acid. So HCl, we have two or more nonmetals. Remember, hydrogen is a nonmetal, even though it's in group 1A. So we have two or more nonmetals, okay? And as a result, we would expect we'd have a covalent compound because we have two or more nonmetals and we have two different elements. Okay, perfect. Looking at P4, so P4, we just have one element. Okay, we just have one element in our formula. However, we have two or more atoms. So because we have a single element and we have two or more atoms in the formula, everyone sees that 4, correct? That means we're dealing with a molecular element. Looking at copper, copper solid, we have one element and we have one atom in our formula. So as a result, we'd call this an atomic element. Finally, calcium oxide, we have two or more elements in our formula, and we have a metal and a non-metal. As a result, this is an ionic compound. Does this make sense to everyone so far? Any questions on this example? Does this logic make sense to everyone? Okay, perfect. So let's apply what we've learned and let's look at the following set of different pure substances. And I'd like you to classify each pure substance as a covalent compound, ionic compound, atomic element, or molecular element. And let's take about 3 to 4 minutes to work through this example, and then we'll come together as a group to discuss. And let's try to get a pool of responses in the chat. And I'd be happy to provide feedback. And if you have any questions at all on this assignment, don't be shy to type your questions in the chat as well. And the responses I'm seeing in the chat look reasonable. Let's try to get a few more responses. And don't be shy if your response disagrees with your classmate. Any response you provide really helps me shape the feedback that I provide students, and it really helps enrich our discussion as we can help address common misconceptions or talk about these examples from an alternative perspective. And we'll discuss this example in about another 1 to 2 minutes. And don't be shy to share your responses in the chat or verbally, or you can ask a question. And the responses I'm seeing in the chat look great. So let's discuss. So nitrogen triiodide. For any chemistry enthusiast, you know this is an explosive substance, and it's commonly either accidentally made during certain reactions, or it can be generated as a byproduct from many chemical reactions, unfortunately. So looking at nitrogen triiodide, we have two or more elements. We have two or more different elements. And additionally, we have two non-metals. So as a result, we classify this as a covalent compound. S8, so looking at S8, we just have one element in our formula, and we have two or more atoms. So we classify this as a molecular element. Aluminum chloride, AlCl3, we have two or more elements, and we have a metal and a non-metal. Aluminum is our metal, chlorine is our non-metal. So already we're starting to apply regions of the periodic table to begin to describe compounds. If you didn't know what the metals and the non-metals were in the periodic table, you'd be a little bit stuck in these problems. So as you notice, we're building on our knowledge that we've established in previous lectures to solve more complicated problems. So aluminum chloride is an ionic compound because it has two or more different elements, and it contains a metal and a non-metal. Xenon. So xenon, so we have one element in our formula and we have one atom. So we'd classify xenon as an atomic element. Does this example make sense to everyone? Does this make sense to everyone so far? Perfect, perfect. So let's now talk a little bit about pure substances and mixtures. We use the word pure substance. What does that mean? Well, pure substance, quite simply, is matter with a fixed, definite composition. So what do I mean by fixed and definite composition? Well, pure substances have a fixed amount of each component element. So pure substances can be either elements or compounds. And the really wonderful thing about pure substances from the perspective of a chemist who wants to actually perform chemical reactions, study the behavior of different elements and compounds, is that the composition of a pure substance is independent of source. So what do I mean by that? So if we isolate pure water, so if we're looking at pure water and let's suppose I isolate pure water and I completely remove all the other impurities and just isolate out pure water from each of these sources. So a glass of water on the desk, water from a lake, water from a dewdrop. If we look at the chemical formula for water, and we look at the water molecules, is there any difference between these water molecules? Is there any drawn difference between these water molecules? Any difference whatsoever? Looking at the water molecules. There's no difference, and this is really important. The composition of pure water is independent of source. Why? Because water is a compound and it is also a pure substance. So the composition of a pure substance, of a pure element or compound, is independent of source. And this is important because that means we can isolate a pure compound, put it in a bottle, label it, and we know that pure water isolated from one source will be identical to pure water isolated from another source. So pure substances have a fixed, definite composition that is independent of source. Okay, and we'll see why we use this definition when we start to talk about mixtures later on. Any questions on pure substances? Any questions on pure substances?
Can you give an example of what's not a pure substance?
Great question. So an example of something that would not be a pure substance, so not a pure substance, that would be, an example of this would be a mixture, where suppose we have a flask and we put, let's say, 10 grams of sodium chloride in 1 liter of water. So this would be a solution of, for example, salt water. So salt water is a mixture. It is not a pure substance. And the reason for that is that depending on how you make your salt water solution, depending on how much of each component you mix together, you will have a variable composition. So mixtures are another category of matter. They're another category of another classification that we use, and mixtures contain 2 or more pure substances. And the key feature of a mixture is that they have variable composition. Another example of a mixture, another example of something that's not a pure substance is if you ever happen to put sugar in your tea or sugar in, as part of any drink that you make, you can put a different amount of sugar. You can put a different amount of each component when you make your mixture. And as a result, that mixture, for example, your salt water or your sugar water, will have a different composition. Does that answer your question?
Yes, thank you.
Perfect. Any other questions on this example? If not, let's keep going now. And we're actually just about to discuss that. So let's recap and let's talk about mixtures. So a mixture is a combination of variable amounts of 2 or more pure chemical substances that are not chemically bonded. Mixtures have a variable composition and contain varying amounts of each mixture component. The components of a mixture are not chemically bonded. Let's look at an example of 2 different subclasses of mixture. A homogeneous mixture has a consistent composition with no phase boundaries. So to show an example of this, let's suppose we have a cup. And in that cup, I'm going to put 10 grams of sugar. And I'm going to put 1 liter of water. So sugar, you can also describe it as sucrose, and it has a discrete chemical formula. So let me give you the formula for sucrose. So sucrose has a formula of C12H22O11. So sugar or sucrose is clearly a compound. And we're going to mix it with water, okay? And as we mix our sugar and we mix it with water, if we let it settle, what we will see is a nice clear solution of 10 grams of sucrose in 1 liter of water. Now, the key features of a homogeneous solution is that if we look at our solution, it is perfectly clear. There is no visible solid. It has a consistent composition. And it has a consistent concentration throughout. So homogeneous mixtures have a consistent composition with no phase boundaries. What that means is we can't see any visible solid in our solution, nor can we see any separation in our liquid layers. We just see a nice, clear solution with consistent composition throughout. Now, you may ask, how do mixtures have variable composition? Well, just like we can easily mix 10 grams of sugar with 1 liter of water, let's say I'm making a tiny cup. Let's say I'm making a tiny cup. In this case, I'm mixing 100 milliliters of water, and this time I'm adding a very tiny cube of sugar. This time I'm just adding 0.5 grams of sugar. That will still give me a mixture. That will still give me a mixture. And it will still be homogeneous. But if we compare these two mixtures, will their composition be the same or different? Did I mix the same amounts of material? Did I mix the same amount of sugar and water in these two cases? No, right? So mixtures have variable composition depending on the amount of each pure substance that you add. Does that make sense to everyone? Perfect. And another thing to keep in mind, there is no bond, no covalent bond or ionic bond between the sugar and water. It's just two pure substances that have been mixed. They're in proximity to each other, but they are not bonded. Okay. So one way that we denote homogeneous mixtures, one symbol that you'll need to remember for homogeneous mixtures is the aqueous symbol. So we'd write this sugar solution as C12H22O11 aqueous. So I'd like you to think homogeneous, aqueous symbol. This is saying we have sugar dissolved in water. Sugar is mixed with water. Does that make sense to everyone? So the aqueous symbol says mixed with water, homogeneous mixture. Okay. Let's look at a heterogeneous mixture. Heterogeneous mixtures, in the opposite case, have an uneven composition and there's a phase boundary between components. So an example of a heterogeneous mixture would be oil and water. So a classic example of an oil-like substance would be hexanes, which would be C6H14. So oil and water, as we know intuitively, do not mix. So if we mix oil and water together, we will see two clear layers. On the bottom, we will have water. And on the top, we will have our oil. which we write as C6H14. So as we can see very clearly, this is heterogeneous. Why? One, there is a separation of phases. And two, this heterogeneous mixture has an uneven composition. Another case where we see heterogeneous mixtures is if we have an insoluble solid. So for example, whenever you see solid state symbols used when something is mixed with water, that's a sign that you're dealing with a heterogeneous mixture. So example, lead chloride solid mixed with water. Lead chloride does not dissolve in water. So if we take our brick of lead chloride solid and we try to put it in water, what we will see is we'll have a layer of water and our lead chloride will just sit at the bottom of our cup containing water. And as we can clearly see, the lead chloride and the water do not mix. We have a heterogeneous mixture. This mixture has an uneven composition and a separation of phases. Okay, so to drive home this idea of separation of phases, let's look at an example where I have a cube of ice in a container of water. So I'm drawing my picture once again. So I have my H2O solid, I have my ice, and I have my cup of liquid water. Now my question to all of you is the composition, is our chemical formula and chemical identity consistent throughout this mixture? Do we have the same chemical formula and the same physical state throughout? And as we see in the chat, no, we don't. So as we see, we have one part of this mixture that has liquid water, the other part is solid water. So we have what's known as a phase boundary. We have two different phases present in our mixture, solid and liquid. This in turn leads to an uneven composition. And as a result, this mixture of solid and liquid water would be heterogeneous. Do these examples make sense to everyone so far? Do these examples make sense to everyone so far? Okay, so let's keep going now and let's talk about the most common subtype of mixture, which is a solution. So a solution is formally defined as a homogeneous mixture where one or more pure substances are dissolved in another set of pure substances. So we call the solute the minor component of the solution. It's the species dissolved in another component. We denote the solute with an aqueous symbol, AQ, indicating the species is dissolved in water. The solvent is the major component of the solution. I like to think of it as the species that is doing the dissolving. Okay, so to give an example of a solution, if we take sodium chloride, table salt, sodium chloride will be our solute in this case. and we dissolve our sodium chloride in a large volume of water. Water, in this case, will be our solvent. Let me label it as such. We, in turn, will be able to generate a solution. So if we add sodium chloride to water, we get a solution of sodium chloride aqueous dissolved in water. So sodium chloride will be our solute and water will be our solvent. So just to recap, so if we're classifying matter, the first question you need to ask yourself, do we have a variable or fixed composition? If we have a fixed composition, then we are dealing with a pure substance. If we have a variable composition, then we're dealing with a mixture. Now, from our mixtures, if we have a uniform, consistent composition throughout, we're dealing with a homogeneous mixture. So we have a consistent, oops, one moment. So for homogeneous mixtures, we have a consistent composition throughout. For heterogeneous mixtures, we have a variable composition, an uneven composition. We see clear separation of phases. So for example, if we look at a mixture of sand and water, it's clearly heterogeneous. There's a difference. The sand and the water do not mix to generate a consistent mixture throughout. You can clearly see regions that have sand. You can clearly see regions that have water. In our pure substances front, the main difference between an element and compound, a compound has two or more different elements as part of its formula. And that is the easiest way, in my opinion, to tell an element and a compound apart. But I do want you to remember, compounds can be decomposed to simpler pure elements. Elements cannot be decomposed to a simpler element. Does this make sense to everyone so far? Does this make sense to everyone so far? Okay, so let's keep going now, and let's first classify the following as a homogeneous mixture, heterogeneous mixture, or a pure substance. So in the first case, we have sulfuric acid dissolved in water, okay? This could also be written as H2SO4 aqueous. Anytime we see the word dissolved in water, that's referring to a solution, and solutions are homogeneous. The next example, we have CH3OH liquid, so that we see that we have two or more elements chemically bonded. We don't have any indication that we're dealing with a solution or a mixture. This is in fact a pure substance. So this is a compound and it's a pure substance. Do these examples make sense? Does this make sense to everyone? So for the last one, first I check the state symbol. Since it's not aqueous, we assume that we're dealing with a pure substance that's not mixed with water. Okay, now looking at our formula for CH3OH, we see that we have two or more different elements and it's part of our formula. So we're dealing with a compound. Compounds, by definition, are pure substances. To answer the question in the chat, yes, we know the first solution, the first mixture is homogeneous because we see the keyword dissolved. Sulfuric acid is dissolved in water, and as a result, we end up with a solution, which is a homogeneous mixture. Does that make sense? Did that address your question? Perfect. Are there any other questions that I can address? If not, let's work on the following example where we classify the following mixtures as homogeneous mixtures, heterogeneous mixtures, or pure substances. And we'll discuss this example in about 2 minutes. And let's try to get a few responses in the chat. And if there are no responses in the chat, don't be shy to ask a question in the chat or verbally. Aqueous means dissolved in water, mixed with water. Sure. We can show an example of a heterogeneous mixture once we finish this example, for sure. Let's give everyone about another minute to a minute and a half on this example, and then we'll discuss. So let's discuss this example. So first, CO2, we look at the state symbol, we see gas, so we're not dealing with a mixture in water at least. And because carbon dioxide has 2 or more different elements, it's a compound, and as a result, it's a pure substance. Formaldehyde, we see this aqueous symbol, which means dissolved in water. And as a result, when we have the dissolved in water symbol, that means we're dealing with a solution, which is a homogeneous mixture. Does this make sense to everyone so far? Okay, so let's now look, so to give an example of a heterogeneous mixture, some common examples that we see in everyday life. An example of this would be cereal. So if we look at our bowl of cereal, we have the milk, and then we have clearly visible solid pieces of cereal. Another example would be like copper chloride solid in water. In this case, we clearly see a difference in the state symbols. So as a result, we see copper chloride is just a brick at the bottom of our water solution. Oh, sorry. The copper chloride is just a brick sitting at the bottom of our beaker that contains water. There's no mixture. There's no dissolving occurring. There's clearly a difference in phase and a difference in chemical composition between our solid copper chloride and our water. Another example would be, as we've seen previously, like oil and water. Or to use another example, if we see carbon dioxide gas and water, actually let's use hydrogen instead of carbon dioxide, just to avoid a potential nuance in that discussion. So if we observe hydrogen gas in water, so we'd have our water and the hydrogen gas we'd clearly see as bubbles. This would be another example of a heterogeneous mixture. In all of these cases, there's a clear difference in chemical composition and a clear difference in phase and physical state throughout our mixture. Yes, if you see two different phases, then it is heterogeneous. Air, so that's a good question. So if we think about air would be an example of a homogeneous mixture. So let me discuss that up here. So if we're looking at air, and if you just take a look in the room around you, can you see any differences in the appearance and composition of the air around you? Do you see any separation of phases? So if you look around in your room, it's very consistent, right? There's no clear separation of phases. So air has a consistent composition. And it has no phase boundaries. And air, in fact, is a mixture. It's a homogeneous mixture of nitrogen gas, oxygen gas, water, carbon dioxide gas. It has a lot of major and minor components, with the major component being nitrogen for those who are curious. So air would be a homogeneous mixture because it has consistent composition, no phase boundaries, and it's a mixture of two or more pure substances. Did that answer your question? Every solid that's mixed with water that doesn't dissolve. So if we see the solid symbol for this part of this class, you'll assume that it doesn't dissolve, so it's heterogeneous. Exactly right. Yes, that would be correct. The only time when this would not be the case, if you see the keyword dissolves in or the keyword a solution. The dissolved in or any words that indicate a solution, you then have to say it's homogeneous. So this is a great stopping point for today. So we'll stop today's lecture recording.